Alright, this is part two of the nature of sound. Again, this is going to be broken into three sections, so hopefully you watched part one first. Now here's part two, and then there will also be part three that you'll need to watch as well to get all of the material that we need for sound covered. So in this video, we're really just going to focus on some of what causes us to perceive sound the way that we do. And the first thing we can talk about, like how high or how low we perceive a sound to be. Some sounds have a high tone, others have a very low tone, with other sounds kind of in the middle. And this whole idea, the tone at which we perceive a sound to be, we call pitch. That's P-I-T-C-H, pitch. And so things have a high pitch or things have a low pitch. In general, we'd say like boys have a lower pitch voice than girls have, and babies have a higher pitch voice than adults have. So we would have these different ways in which we can talk about the pitch of a voice, but it really refers to how high or how low a sound is perceived to be by its tone. Now, its frequency is this other thing that we've talked about, and it's really is a measure of the number of waves that are produced over a given amount of time, and it's expressed in the unit hertz. So we have like this area here, if we're looking at this wave, this area here where particles are really spread apart, we call this a rarefaction. And then an area here where particles are squeezed close together, we call that a compression. So I have a rarefaction, compression, rarefaction, compression, rarefaction, compression. So this indicates to me that if this whole thing takes just 1 second worth of time to be produced, then I have one full wave cycle, which includes a rarefaction and compression, another complete wave cycle, rarefaction, compression, and a third complete cycle with a rarefaction and compression. So this would be 3 hertz, or 3 waves produced in 1 second, because a hertz is equal to 1 wave produced in a second. And it's the frequency of a sound wave that is ultimately responsible for the pitch that we hear. So a frequency that's very high will produce a very high pitch. A frequency that is very low will produce a low pitch. So if we look at just a keyboard here or a piano, this middle C, which is kind of a common place that people use to identify where their hands are on a keyboard or piano, this has a specific frequency of 261.62 hertz. Anything that's above that frequency is going to be a pitch that is higher than middle C. Any frequency that's below that is going to be a pitch that's below middle C. So if we were to look at like 3 tuning forks, where the first tuning fork had a pitch that was high, then we would say, well, its frequency is high. But we also know about the relationship between frequency and wavelength. So if the first tuning fork has a high pitch, then it would have to have a high frequency and a short wavelength. So high pitch would be high frequency, short wavelength. If we had a tuning fork that had a pitch in the middle, it's going to be a middle frequency and a middle wavelength. And if we had a third tuning fork that had a lower pitch than the other two, it would have a low frequency and a longer wavelength, because frequency and wavelength have an indirect relationship or inverse relationship, that as frequency increases, wavelength decreases. Pitch and frequency have a direct relationship, so as pitch increases, frequency increases. This also means that pitch then has an inverse relationship with wavelength, that as pitch increases, wavelength decreases. So you should kind of be aware of those relationships between pitch, frequency, and wavelength. That's really not anything new that we've talked about. Now, if you had the opportunity to kind of look at our textbooks that we have in the class, or if you looked at the online textbook, there's charts that have some different animals that can hear different frequencies, and this kind of set list of animals, and there's a whole bunch of them. Some organisms we notice have not only can hear higher frequencies, but some different animals can hear really big ranges of frequencies. So some animals that can hear like really, really high frequencies, higher than what humans can hear, are like the bat. So a bat produces really, really high frequencies, and it hears high frequencies that we're incapable of hearing. Now, some of the sounds that a bat makes are still within the range of what humans can hear, but some of them are not. Other animals have really huge, wide ranges of sounds that they can hear. So maybe they can't hear quite as high as a bat can hear, but something like a baleen whale can hear much, much lower tones than a bat can hear. So this is going to be a baleen whale can produce and hear sounds much higher and much lower than what a human can hear. Now, when we look at what these ranges are, the range that humans are said to be able to hear is 20 hertz to 20,000 hertz. So if you think about what is like considered to be like perfect vision, is 20/20 vision. Well, perfect hearing would be like 20/20, but it's 20 hertz to 20,000 hertz. This K is 20K, 20,000 hertz. So anything that's below that range of hearing, below that range of frequencies, is too low a sound for a human to hear. And so we call this infrasonic, where that prefix infra means below. But then any sounds that are above 20,000 hertz we call ultrasonic, and these that prefix ultra means above or beyond. So sounds that are ultrasonic are too high a pitch for us to hear, and anything that's infrasonic is too low for us to hear, with our sweet spot being from 20 hertz to 20,000 hertz. Now, it's a little misleading to say that human hearing is 20 hertz to 20,000 hertz, because that might be the case when you're like very, 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 very young, but that quickly kind of dissipates, and you don't have the same range of hearing. So I, for instance, can hear from about somewhere around 150 hertz on the low end to about 17,000 hertz on the high end, maybe not quite that high. So there are range within that 20 hertz to 20,000 hertz that I don't hear anymore. And as you get older, that continues to happen. You lose more and more and more of those ranges of hearing. So there's certainly the possibility of someone younger than I am, like a student, hearing sounds that I can't hear anymore. If you're curious to what your range is that you can hear, there's like all sorts of apps that you can download for your phones that produce different sound frequency levels, and you can kind of tell, you can get an idea of what range of sounds you can hear. I've noticed with most of my students at this point, we're looking at somewhere around 100 hertz on the low end and 18 to maybe 19,000 hertz on the high end. But anything that's below 20 hertz is considered infrasonic, because 20 hertz is considered that human range, even though in reality most of you are not going to be able to hear that low a frequency anymore. And anything above 20,000 hertz is considered ultrasonic, because it's above the range of human hearing, even though we recognize that 20,000 hertz is probably not really realistic for most people that are more than a handful of years old. And it gets worse as you get older, just due to exposure. Lots of loud sounds can damage your hearing. You can lose some. If you had ear infections, that can cause hearing damage to your ear or things like that. So that's part of why it's such a bad idea to, I have students that put their headphones in and crank the volume all the way up, and I can be 20 or 30 feet and I can still hear sound coming from those headphones. That's sitting right on top of your eardrum is certainly probably doing some damage, and you'll probably end up losing some of those range of hearing as a result. So that's probably not a good idea to do. So that's it for this part 2 of our sound notes here, our nature of sound notes. So make sure you check out the third video, and if you have not already checked out the first video, please do that as well.